there we go. Cool. Yeah. Well, thank you for coming. Thank you for sticking around, and thank you for putting together this amazing workshop. It's so good to see all these familiar faces, good old friends, and some new ones as well. Uh, so since this looks like a pretty manageable sized crowd, I was hoping that maybe we can like take all the questions on the fly, especially since this topic is going to be like a little bit strange, I guess, for most people. There's going to be like many concepts that are typically not familiar for like really any audience that I speak in front of. Yes. Okay. So this is a workshop on control and reinforcement learning. And I'm looking at the crowd, and it looks like a very different composition as a workshop that I was at 2 weeks ago in Banff with almost the same title. That was almost entirely dominated by control people. Uh, is really funky because I was ready to like explain all of the semantics and all the details and all the technicalities in this talk, and they immediately understood everything. It was like the most bizarre thing that I ever experienced. Because in my experience, reinforcement learning people need a lot of time to get used to what this talk is about. So please ask me questions on the fly. I'm gonna really appreciate that. And also let me add that even if you think that you have seen this talk before, this is a slightly different talk. Actually, it's quite different from the version that I think Tim has seen last summer, or Walter. So yeah, in case you want to go to sleep, well, tough luck. Right. Okay. Cool. So this is based on joint work that we've been doing with friends in Barcelona, Sergio, Anders, Ludovic, and Javi. And it's about trying to answer the following question. Imagine that I have a bunch of stochastic processes, a bunch of Markov chains to be specific. I want to figure out a way of comparing them. I want to figure out a way of quantifying the intuition. Is that, okay, if I look at the realizations from this random walk, and look at this random walk, these look kind of similar to each other and more similar. For example, like this one looks more similar to this one than it does to this other one over here as well. And this one looks more similar to this one than it does to the other one. So I want to find a way of quantifying this similarity or defining similarity metrics between stochastic processes. And in particular, I'm gonna explain how this figure was generated. So this is an embedding of distances between pairwise comparisons of stochastic processes, and this is this is an image that correctly captures these similarities that I was explaining. So the reason that I'm talking about this and my motivation to study this problem is really related to reinforcement learning, and in particular representation learning for reinforcement learning. So the question of representation learning, I know that this is like a very overused word, but the way that I understand it here is as the following question. Imagine that I have a sequence of observations that are high dimensional, complicated, let's say like sensor observations or like, you know, images, radar, video, sound, whatever. So there's a sequence of X's, and I want to find a low dimensional representation of the same process that is, in a sense, close enough to the high dimensional one. So for example, if I'm looking at this picture, you can see that this sort of low dimensional representation is capturing something meaningful and hopefully important about what is happening on this left picture as well. And this is sort of important if I want to build reinforcement learning agents that are able to work with high dimensional observations, because I have a hope that maybe I'm going to be able to learn behavior policies in the low dimensional space more effectively. So this is my motivating problem. This is the reason that I care about comparing processes. And the question that we are trying to answer is, okay, but how do I define close enough, right? So in what sense do I want the high dimensional process to be similar to the low dimensional process? What is the meaning of these words, close enough? How do I mathematically tackle this question? And how do I compute such similarity metrics? Right. Okay. So I hope that you're all motivated. So this is the outline of a previous version of this talk that I've given before. I'm going to give you some ways of defining distances between Markov chains, and after cycling through a few failed attempts, I'm going to give you something that I believe to be the correct distance. Of course, we can debate later about whether or not this is like truly correct or this is the best distance that one can define. And then I'm gonna give you some ideas as to how to compute such distances. So this second half of the talk, this is based on a paper that we have written last year, but in the meantime, there has been some progress on this problem, and there's some new content that really hasn't been seen by anybody so far in the talk, which is about stochastic optimization methods for computing optimal transport distances between Markov chains. If there's time, we're gonna have some pretty pictures as well. All right, cool. So let me just jump into the definitions. Who knows here what a Markov chain is? Okay, I guess the others are sleeping. So, because I think everybody knows what the Markov chain is, or everyone should know in this crowd. So this is really just to fix the notation. The Markov chain is a stochastic process, which is a joint distribution over an infinite sequence of states. Each state takes values on a finite state space X, finite only for simplicity. The process starts from a fixed initial state X naught, and the evolution of the states is governed by this thing that I call the transition kernel, which gives the probability of transition from state X to X prime. And this is assumed to be stationary, so it doesn't change with time, as a stereotypical picture about the evolution of the states. So of course, we all know this model for a variety of reasons. I guess people coming from a reinforcement learning direction know it because this is the standard modeling tool in reinforcement learning, and it has a bunch of applications within reinforcement learning. For example, it can accurately model classical applications like sequence of screens in a video game, or sequence of observations from a physical sensor, or maybe in theoretical computer science, it can model a sequence of memory states of a computer program, or even you can think of just random walks on the real line, or queuing systems or whatever. So this is something that has been extremely successful, extremely popular. So I don't think that this motivational slide requires all that much more explanation. So let me just jump into the concrete setting that we are looking at in this work. So I'm going to consider the following problem. I have two Markov chains denoted by mx and my. They live on potentially different state spaces, x and y. You can think of it as x being a very large state space and y being a small state space, right, in the representation learning example. But you can also think of them as being the same for certain running examples that I'm going to have. They're obviously going to have different transition kernels denoted by px and py, and the initial states are going to be denoted by x naught and y naught. And in order to define distances between the stochastic processes, these joint distributions over infinite sequences, what I assume is that I have a way of comparing individual states in the first place, right? Because if I cannot even compare individual states, then how can I hope to compare sequences of states or joint distributions over infinite sequences? Yeah.
There is a similar problem, distance between probability density functions.
Mm-hmm.
Can you please comment? I do not know, that's why I'm asking.
Yeah.
What is the difference between computing distances between two density functions or cumulative distribution functions and processes?
Yeah. So this talk is about like similar methods, right? So you probably are thinking about Wasserstein distances or optimal transport distances. So those are classical ways of lifting distances from state spaces to distances between distributions over the state spaces. Here, the method that you're considering is lifting this distance between individual states to joint distributions over infinite sequences. So this is going to be a kind of version of that. So maybe I'm going to give you the definitions, and then we can get back to this to clarify.
Please comment which one, you can do it later, which one is more difficult.
Yeah. So let's get back to this later. Yeah. Because I think a few of these questions are going to be answered. Right. Okay. So I imagine that I have a way of comparing individual pairs of states, x's and y's, and that is going to be done by this thing that I call the ground cost function that maps pairs of x's and y's to real numbers. And this is a way to quantify dissimilarity between x and y. For example, if the two spaces are the same, d-dimensional Euclidean space, then, for example, a suitable cost function can be just Euclidean distance between x and y. But a more abstract and often more useful way to define cost functions is in terms of a labeling function L. So labeling function assigns labels to X and Y, and I can define then a cost function in terms of this labeling function. So if the labels associated with the two states are the same, they are at distance 0, otherwise they are at distance 1. Or even more interesting for us that are into reinforcement learning, an interesting case is when I have reward functions that are defined over the X and Y spaces. So if I have Markov reward processes, which is a pretty frequent scenario that you encounter in reinforcement learning, then I can define my cost function in terms of the reward functions, right? So really just a comparison between the reward associated with X and the reward associated with Y. So there are many different ways of defining a cost function. I'm going to assume this as being given to me during this talk. Yeah.
So you have said that similarity between states is what you want to measure. So do you need a metric or semi-metric? Or rather, that probably a metric.
Right. Yeah. So if my cost function is a metric, then the notion of distance that I'm going to define is going to lift this to a semi-metric over Markov processes. Right. Much like the Wasserstein distance is a semi-metric as well. All right, cool. So this is the setup. We got two Markov chains. We got a cost function to compare states. What do I want to do? So I wanna figure out a way of lifting this distance to the space of processes, and I wanna figure out a way of distinguishing between Markov processes. And in order to go through a number of ideas and arrive to a correct definition, I'm going to use these two running examples of Markov processes. The first one is something I call scramble. This is really just an IID sequence of integers between 1 and 10. So this is just like a complete mess over here, complete IID sequence of integers. And this other process is what I call sawtooth, which just cycles through the same integers in order. So it just 1, 2, 3, 4, 5. And then once it reaches 10, it just drops back to 1 and so on, right? And it has this sawtooth shape. Obviously, both of these are Markov processes because the next state is fully determined, or the distribution of the next state is fully determined by the current state. And the ground cost that I'm going to be considering in these examples is simply this Hamming distance, which is 0 if the two states are identical and 1 otherwise. So obviously these two processes are not the same, right? So I want to have a distance that is going to correctly distinguish between these two and point out that these are not the same processes. And there are also some other issues that are going to pop up on the fly that I'm going to explain. So every time I start talking about this problem with people, they suggest that, oh, okay, so you could just consider the stationary distributions of the two processes and just compare them, right? So the stationary distribution of let's say the process X is really just the long-term average distribution that it generates over the state space, right? So this is the average number of times that the process visits state X. And then what I could do is that, okay, I just compare the stationary distribution for the X chain, the Y chain, and just compare those stationary distributions. For example, in terms of the Wasserstein distance. Yeah. Say again? If you define it like this, well, yeah, you can define it in terms of like a Cesaro average, and then it does have a stationary distribution. But since you're talking about this, what do you think the stationary distribution would be for that?
Well, I'm assuming you end up with you use this definition you say for uniform.
Yeah.
But the definition of stationarity, not just convergence, but limiting distribution, is different since you assume well, in this periodic it should exist. One of the four conditions of the class.
Yeah, right. So like a periodic process, it's kind of iffy, but this limit actually exists for that process. And then this discussion already points out a problem with this definition is that if I look at these two examples, scramble and sawtooth, then I immediately notice that they have the same stationary distribution, right? It's all uniform on 1 through 10, right? Because it all visits, both processes visit state 1 with probability 1 over 10 on the long run, or state 2, 1 over 10 on the long run, and so on. So both of the stationary distributions are the same, and this notion of distance is not going to be able to distinguish between the two processes. So this is a bad idea, obviously. So let's try to fix this. Let's try to do something else. So this is idea number 2. Let's do the following. Let me run the 2 chains in parallel, right? So let me consider independent realizations of the 2 processes and look at the discounted sum of the costs between the xt's and the yt's, right? So let me just run these out to infinity. Let me look at the distance between the individual states, and let me discount it for the sake of convenience with some discount factor gamma. So the problem with this is that even if the 2 processes that I'm trying to compare are very similar to each other, if I run the 2 chains in parallel independently of each other, then basically, the 2 chains are going to diverge almost immediately if there's any degree of randomness in them, and I'm always going to be putting the 2 chains at like a constant distance from each other. Right, so here, the fact that there can be randomness in the trajectories and the randomness is independent, I'm going to see trajectories. So this is the blue curves are trajectories that are generated from mx. The red curves are trajectories that I generate from my. And you see that if there's any randomness in them, they're going to diverge from each other, and then I'm lost, right? So even if the 2 processes are the same, this is not going to give me anything meaningful. In particular, if I consider this scramble Markov chain, the distance between scramble and scramble is going to be a large constant. So this notion of distance is not going to be able to detect and deal with this problem. We see that here the problem was that I ran the 2 chains independently of each other. So here's the idea. Let's allow the 2 chains to share some randomness, to share random coin flips, and allow them to share their coin flips in a way that allows them to move as much together as possible. So in particular, if I consider couplings between the 2 chains, so for example, if I repeat the same experiment and I try to allow the 2 chains to share coin flips, and I try to do this in an optimal way, then I'm going to see trajectories like this, right? And these 2 processes are very similar to each other. And this is going to correctly recognize this fact over here, right? So what is this mysterious notation over here? This pi. So pi of mx and my. So this is a coupling of the 2 processes. It's a so-called causal coupling of the 2 processes. You need to think of this as a Markov chain over the joint state space x and y, such that if I look at the x component of these joint sequences of states, that is going to correspond to the chain x, right? And if I look at the y component of this joint Markov chain, then that is going to be the y process. So this is going to be, so it's obvious that I can define such a Markov process, and then what this distance is telling me to do, or what this formula is telling me, is to, among all the possible couplings between 2 processes, I'm going to choose the coupling that minimizes this cumulative cost over there. So to allow the sharing of the randomness between the chains in a way that minimizes this cumulative distance over time. So this is a so-called, so this solves both of the problems that we have seen before. This correctly distinguishes between scramble and sawtooth, because there's no way to couple together scramble and sawtooth such that they would be at a distance that's anything lower than 9 over 10. And it correctly recognizes that that 2 instances of scramble are at distance 0 from each other, because I can just simply set xt as being equal to yt in that scenario. Right. So this is a so-called optimal transport distance. This is a mathematical topic with a very long history and with a lot of beautifully deep results. There's this book by Cedric Villani from 2003. It's a 1,000-page book, and it's full of very heavy math. And the specific problem that you're looking at is optimal transport distances between Markov chains. So this is a relatively recent topic of investigation that I think was first studied in 2021. And then a sequence of, and then a bunch of people jumped on this. Turns out that what was established in these early works is that such an optimal coupling, so solving this infimum problem over here, can be equivalently written as the solution of this system of equations that I think should be very familiar to both to all of you. This is really just the Bellman optimality equations, or something that's analogous to the Bellman optimality equations for the control problems that can be associated with this optimal coupling problem. So so you don't really need to parse all of this formula here. There's some infimum on the right-hand side that appears in the Bellman optimality equations that I'm going to get to in a second. So so this is really just like a fixed point equation, a high-dimensional nonlinear fixed point equation, where there's a nonlinear operator that appears on the right-hand side. Yeah.
I just was thinking about previous slide, and comparison of two processes could be too much of information. I just was thinking that we mathematicians, we consult industry, and they need just one quantity. They do not need all 1,000 realizations, all moments.
Right.
So actually already comparison of two probability densities, it's maybe unnecessary. We can compare mean values, variances, maybe it's enough. So I was also thinking, what motivation is compared to processes? Maybe we should compare only some scalar quantities.
Right. So I guess if you just go back to this example, right? So here you want to have a quantity that is able to correctly say that this process or this sequence of random variables is behaving differently from this sequence of random variables, right? My original motivation for this is representational learning, where I want to learn a representation for a high-dimensional stream of video, right? So I want to compress something super high-dimensional to something that is low-dimensional. And if I just want to match the moments, or if I just want to match, I don't know, like the distribution of mean values of pixels or variances or whatever, then I'm just going to get useless representations. So I really need something that takes into account the temporal behavior of the processes. And for that, I really need to consider the entire infinite sequences in my definitions, if that makes sense. Yeah. Right. Yeah. Right. Yeah. Sorry. So here, this gives an expression for the distance between the two chains if the initial state is x and y. So if the initial state for x is little x and the initial state y naught is equal to y, then the distance satisfies this system of equations as a function of x and y. Right, so that's all good. And when I was giving this talk in front of a bunch of mathematicians, they were like, okay, so everything is done. What else do you want from this? Because this uniquely characterizes the solution and everything. The problem for us computer scientists is that this system of nonlinear equations is just really horrendously expensive to solve. And that is because on the right-hand side, there's this infimum that is like really, really complicated to calculate. That's an optimal transport problem. And if you want to use this Bellman equation as a foundation for a dynamic programming value iteration style method, then each application of the Bellman operator will require solving this infimum, and that is really expensive. You don't want to do that. So this is what motivated us to look into this problem from a computational angle and try to come up with algorithms that are going to be able to solve this problem without dynamic programming, and hopefully in a way that allows us to use data as we want in machine learning. Right, okay, yeah, so I already given you most of the motivating examples, especially this representation learning example. People have been looking at similar problems with other purposes as well. For example, if you're able to define distances between Markov chains, that allows you to define distances between other objects as well. For example, graphs. I can compare graphs by running random walks on the graphs and reasoning about the similarity of the random walks. as a measure of similarity for the graphs. Another interesting motivating example is something that comes from concurrency theory, formal verification, which is a branch of theoretical computer science, where people are interested in comparing computer programs or implementations of computer programs. Just imagine that the X and the Y chains are implementations of, well, let's say the two programs, where the states correspond to internal states of your computer, you know, the contents of the registers, the memory and whatnot. So there, you don't really care about what those two implementations are actually doing in the registers, how they are shifting around the bits, right? You don't say that they are equivalent if they are doing the same thing at that hardware level. You care about what they write on the screen, right? And that is a labeling function that you can use for defining a cost between memory states. And people have been looking at that since the early 80s, where this distance that I've been talking about is called bisimulation relation and bisimulation metrics. So that's another motivating example. Right, okay, so let me give you some algorithms now. Hopefully you understand the problem and you're motivated. Okay, so let's do this. So our journey in this topic started with this paper that was published last year in NURBS with the same set of authors, Sergio, Anders, Ludovic, and Javi. In this paper, we observed a bunch of really useful things. So we pointed out that this optimal transport distance that I've just defined is equivalent to a concept that's called bisimulation metrics from theoretical CS that has been used for formal verification in the past. And it has been somewhat popular in reinforcement learning for representation learning. And we had a bunch of technical results as well. In particular, we managed to develop an algorithm that has convergence rates, computational complexity, guarantees, and it does the following. It takes as input two transition kernels, PX and PY, and a ground cost. And it based on some adaptation of algorithms for optimal transport and entropy regularized Markov decision processes, it implements the certain dynamic programming scheme that we call sinkhorn value iteration with all sorts of beautiful guarantees and stuff. So it was a lot of fun to write this. We learned a lot about this, and we are really happy with the results at the time. But you know, there's a big limitation for all of us that are trying to do reinforcement learning with this or representation learning for this, which is that this method requires perfect knowledge of the transition kernels PX and PY. And it's really just a dynamic programming method. And we had like a really hard time trying to turn this into an approximate dynamic programming method. We tried really hard. We did not manage until we had the right idea. And that is based on the following observation. So for a given coupling pi, which is, again, just like a joint Markov chain on the state space xy, I can rewrite my objective. You remember that I want to calculate the infimum of this over couplings pi. So for a given coupling pi, I can rewrite this infinite sum in this form. See, this is really just using the definition of the expectation. And then, you know, as every engineer does, not necessarily a mathematician, but as every engineer would do, my first instinct is that every time I see two sums, I want to swap them, right? Let's say we can do this. We can do this because, you know, finite state spaces and so on, convergent series. And then I just look at this expression again and say that, okay, so maybe this quantity over here is of some special interest, right? So this quantity over here, which is the discounted number of times that the coupled process is going to hit state pair X and Y, this is something that allows me to rewrite my objective in a nice linear way. You see that my objective is really just an expectation of the cost function under this joint distribution. So this is what I call the discounted occupancy of state pair XY under the coupling pi. This is really just the discounted number of times that the process visits this pair of states. And this reveals some hidden linearity in the problem, right? That was not obvious in the first place, right? So this is something that allows us to reformulate our problem as a problem of linear optimization, all I gotta do now is minimize in the space of occupancies, find the occupancy that is going to minimize this expectation. Here. Yeah. Yes, technically this is necessary for now. I'm sure that this can be worked out correctly for infinite state spaces as well, but I'm not like a proper mathematician. I don't know how to do continuous stuff. All right, this is really great company.
What's the meaning of pi?
Right, so pi is a coupling between two processes, which is a Markov chain whose state space is the product space of x and y, right? And it is such that the marginal distribution of the x's is the x Markov chain, and the marginal distribution of the y's is the y Markov chain, if that makes sense. So you can think of it as really a way of coupling together the two chains and allowing them access to joint shared coin flips, essentially. Yeah. All right, good. So we have discovered this hidden linearity. How can we use this to define or design algorithms? So let me give you the gist of our approach. For that, I'm gonna need this slightly adjusted definition of the occupancy coupling. So an occupancy coupling of a coupling pi is the discounted number of times that the process visits state pair x, y, followed by x prime, y prime. I need this joint distribution for technical purposes in the future. It's really the same concept as we have seen before. And turns out that, that these occupancy couplings have three properties that perfectly define them. And these properties, so this is some design ideas by PowerPoint, very primitive AI. So it's a coupling property. It satisfies a so-called causality property and a so-called flow property. So let me walk you through all of these, and this is going to take us to the payoff. So first, the first property of occupancy couplings is a so-called coupling property. What this one says is that the occupancy coupling should be a coupling of the marginal occupancies of the x and the y chains. So let me explain what this is. So this new x of x and x prime, this is just the total discounted number of times that the x process visits state pair x prime in time steps xt and xt plus 1. New y is the same thing for y. This is the discounted number of times that the y process, the individual marginal y process, visits y and y prime in consecutive steps. And obviously, the coupling property of the occupancy coupling is that if I marginalize out the y's from the joint distribution, that should be equal to the new x. And if I marginalize out the x's from the joint distribution, that should be just the new y. Right. So this is what I call the coupling property of occupancy couplings. Another property is what I call causality, which says that if I look at the conditional distribution of x prime and y given x that is induced by mu pi, this is like the conditional distribution that is defined in the obvious way from mu pi. So that needs to factorize in this form. So the probability of seeing x and then seeing x prime and y prime should factorize in this form. That it should be a product of the transition kernel and some other distribution mu pi y given x. And the conditionals for y prime x given y should satisfy the same form as well. So this is somehow telling that there should be no shared information between the future y prime and x given y. Like y acts as a separator between these. So if you fold the two constraints that I talked about together, the coupling and the causality constraint, then they can be equivalently written in this form. Well, this is just algebraically equivalent. You can derive both constraints, both conditions from this one. There's no serious need to understand the math. You can just believe me that this is true. And then finally, a constraint that should be familiar for people that come from control or statistical physics, which is a so-called flow or detailed balance condition. And this essentially means that whatever probability mass flows into a tuple of states x prime, xy is the same as the probability mass that flows out of that space. So this is a type of flow constraint that is satisfied by path distributions or stationary distributions, if you want. Right, okay, so let me just put all of this together and state this result to you. We can talk more about that, I guess, after the talk, or if you have more questions, I can answer them later. So here's the main theorem that is underlying our main result. So this one says that the set of all possible occupancies that can be ever induced by any coupling between the two processes is uniquely characterized by these constraints. So every mu should satisfy the flow constraints. Whatever mass flows in should be the same as the mass that flows out. And it should satisfy these coupling and causality constraints as well. So that all of the stuff that I explained holds. So what this gives us eventually is that the distance that I've defined, the optimal transport distance between the two processes, can be written as this as the solution of this constrained optimization problem, which can be written using the method of Lagrange multipliers, using this as this min-max. So the distance is equal to a minimum of this Lagrangian function with respect to the primal variables mu and lambda. Mu are occupancies and lambdas are conditional distributions, and the maximum over dual variables alpha, beta, and v, which penalize the deviations or violations of these constraints. And the Lagrangian itself is defined as this. I know that this looks pretty horrible to look at, so there's a simplified form that I've prepared for your convenience over here. This one says that the Lagrangian evaluated at mu lambda, the primal variables mu lambda and the dual variables alpha beta, can be written as a sum of three expectations. The first is an expectation with respect to mu, the primal variables mu. The second one is an expectation with respect to nu x. And the third one is an expectation with respect to nu y. So these can be computed based on sample trajectories from the two Markov chains. And this is the important feature that makes this whole approach click. So there's these expectations, like everything can be written as an expectation, which means that I can just solve this by stochastic optimization. I can solve this problem, this min-max problem, by doing stochastic gradient descent for the primal and the dual variables, thanks to the fact that my whole objective is written as an expectation. So this is what motivates our algorithm. Again, I know that this is a lot of formulas to look at, and I was just about to have a nap before giving this talk, so I imagine that you must be in a pretty similar state of mind. So let me just say that this algorithm is just primal dual gradient descent or primal dual stochastic gradient descent for the two sets of variables. So there's two players, if you want. One that is controlling the primal variables, trying to calculate the minimum with respect to mu and lambda. And simultaneously, there's another component to the algorithm that tries to do stochastic gradient ascent on the dual variables, alpha, beta, and v. So these two algorithms are calculating updates to the parameters simultaneously and trying to calculate the setup point, which is the solution of the constraint optimization problem. We call this algorithm stochastic optimization for Markov chain optimal transport, or SOMCOT. And notice that, or the one thing that I really want to highlight about this, and this is the one that took a lot of work for us, is to figure out a way of running this algorithm in a way that only requires samples from the occupancies of nu x and nu y. Notice that these updates never need to query the transition kernels in fixed states x and y. It doesn't need random access to the transition kernels px and py. It doesn't require generative models. It only requires sample trajectories. Like in particular, these x and x prime and y prime samples are used to calculate the updates to the dual parameters over here. Yeah, so this is why all this gymnastics was required to set up this primal dual method. Right, so we got some sample complexity guarantees and runtime guarantees. this algorithm is guaranteed to output an epsilon accurate estimate of the optimal transport distance after this many iterations, after 1 over epsilon squared many iterations. And the scaling with the number of states is actually surprisingly good, because I would have expected xy squared in this one, since that is the number of unknown parameters that you would need to estimate. The actual scaling that we got is xy times x plus y, which is like a little bit more benign. So we are really happy with this because this is actually the absolute first result of this kind. No previous algorithm was able to calculate optimal transport distances between Markov chains before based on sample trajectories only. Every previous method required perfect knowledge of the transition kernel. We got this result through a regret analysis of the primal and dual players directly. And notably, this big O, it doesn't hide any problem-dependent parameters or any nasty assumptions, only a numerical constant, which is, I don't know, like a 100 or something like that. And maybe there's some log X and log Y factors on top of this. Right, so on the theory side, we are really happy, yeah. Uh-huh.
The xk, xk prime from UK,
Mm-hmm. Right. Yes. Yes. So, so technically, this result holds when you have IID samples from the occupancy measures, which is like a little bit painful to generate because you need to go to the initial state, run your process for a geometric random time, use that sample, and then reset your process to the initial one. But in practice, you can just use like all the samples that you want. You can use dependent samples, and that should work fine.
How is the sampling from you? Like,
Oh yeah, so from mu you can sample because that is your own, that is under your own control, right? So mu k is this distribution that you maintain over x, y, x prime, y prime. So you can just sample from this directly.
you have to also kind of stabilizers.
No, you don't need to assume. I mean, you just sample this xk tilde, yk tilde, all of this from the current mu k, right? So you can just sample on the fly. No need for averaging or 2 time scales or anything like that. Just on one single time scale, you can just run them in parallel. And it's all fine. All right, okay, so I'm not sure how I'm doing with time, but maybe there's gonna be some time for... Okay. Yeah, I don't want to make Andreas miss his flight, so let me just rush through the pretty pictures. Yes. Let's see. Okay. So representation learning, right? So this was my motivation. So let me just show you some experiments that we have done to sort of validate that this idea makes sense for representation learning. This is really just a proof of concept. And for that, we're going to use this abstract setting that we call block Markov chains. I don't know if you heard about block Markov decision processes. It's an abstract setup for studying representation learning questions. So in particular, what we look at is this setup that I have 2 chains. One is just a random walk on the integers 1 through 10 with a bias theta. That is the probability of going up. You go down with probability 1 minus theta. And there's an additional chain my, which is a process with a larger state space, 5 times as large state space, where the states correspond to xt. And some uniformly randomly chosen additional noise variable that is added on top of the xt's. So it's basically like a noisy observation of xt from which, in principle, you could decode what the original xt was if you knew the mapping from x's and y's. But in practice, you don't know this. And this is typically the case when you're, for example, looking at the screen of a video game that has like a lot of like, random colors and like a bunch of like background that is irrelevant to the decision-making task that you're trying to solve. Right, so we ran some simple experiments on this one, and that was fun to do. So this is one set of experiments where we considered a sequence of realizations from this Y process, which is just a simple low-dimensional process with some additional noise. That was generated by some fixed theta star, that was 1/2. And then we considered a bunch of candidate processes to try to fit this low-dimensional process xt to the high dimensional process YT and we realized, and we generated a bunch of trajectories for a bunch of different choices of theta and compared it with the sequence of y's using our method. And we computed these distances, and this is the picture that we got after different sample budgets and different runtimes. So you see that that this method, after essentially like 1,000 iterations, was able to pick out like what is the correct parameter theta that might have generated the two process. And the more and more iterations we run, the closer and closer we get to the ground truth distance. So this serves as like a bit of as a bit of a proof of concept that this method can indeed detect these hidden structures in representation learning tasks. So let me show you something that I think is even more interesting. This is like a little bit more technical and requires like a tiny bit more understanding of what this method is doing. But so if you go back, sorry for just zipping past the whole thing. So if you look at this Lagrangian, this horrible optimization problem, the primal variables lambda, these are conditional distributions of y given x and x given y, right? So these are, so if I run my optimization algorithm for a while, that computes like the optimal mu, the optimal lambda, alpha, beta, and v. The optimal lambdas, the lambda x and the lambda y, they can be seen as the optimal coupling between x and y, and the optimal coupling between y and x, or sort of like a mapping from y and x and a mapping from x and y. Or in other words, that is popular choice of words in representation learning, I can think of these two distributions as encoder-decoder pairs, right? I can think of this as the distribution of the observation y if I see x, and the distribution of the true underlying state x if I'm observing y. So I can think of these as encoder-decoder pairs. And we did this really funky experiment on this block Markov chain example, where we just collected observations from a coupled process x and y, and ran our algorithm on top of this for different sample budgets. And we see this beautiful encoder-decoder structure emerging from the process. So you see that the optimal one should be this diagonal structure that emerges after like 10,000 iterations. It should be such that for every x, I should have a uniform distribution over the generated y's, and for every y, I should have a point mass on the corresponding x, and that is the structure that has been emerging from these experiments. So I think that this is a very powerful observation that is going to be important for future applications of this process for representation learning. So this is probably something to keep in mind. Right, okay, so let me conclude because I don't think that I have all that much more time. So I'm really excited about this because in this work, we have finally managed to hack this problem of how to compute distances between stochastic processes based on sample data only, based on observational data only, without knowing anything about the process laws, the transition kernels, and so on. And we really believe that this should be very useful for representation learning. And one reason to believe that is that actually the failed idea number 2 that I mentioned about running out the two processes in parallel and comparing the costs on the fly, that is exactly the loss function that is optimized by mu0, which is like one of the most popular representation learning methods for model-based reinforcement learning. So since that has been working so spectacularly, I would think that if you use the correct version of that distance that allows couplings on top, then maybe you can do even better. Right now, what we're thinking about is how to scale all of this up, right? Because we have seen that everything only works so far for the tabular case, for discrete state spaces. We have some ideas as to how to introduce function approximation into this, but those are pretty rudimentary, and this is like pretty open-ended right now. Another interesting topic that is, again, going to be, I think, really, really important for future applications of this is that one can notice that the distance metric that we have is actually differentiable with respect to the representations, because it's a solution of the linear program, and the dual variables alpha and beta they are actually the derivatives of the distance with respect to the occupancies, with respect to the occupancy couplings and the transition kernels. So I think that this is also something that's going to be potentially very important. And well, everybody can come up with extensions of this and ideas. I think that this is a pretty hot topic that is emerging and hopefully going to be well, useful in the future. And I hope that you found this reasonably interesting. If you have questions, then just please let me know. I'm going to be around for today and tomorrow and tonight as well. So yeah, thank you for your attention.
Yeah, thanks, Gargo, for the nice talk, as always. So any question?
Thanks for a nice talk. I've a maybe very basic question, but I've been kind of thinking about the role of the what do you call it? Base costs, I think. So in the representation learning case, right, kind of I don't know kind of in the embedding space what should be close to what. So I was wondering if you could comment on that and maybe kind of tell us a bit about what you used in the little example at the end. Maybe that helps understand.
Right. Yeah. So I guess in reinforcement learning, the cost that you want to use is this, right? And in reinforcement learning, I guess like the use case is that I have some high dimensional process, right? And I use a state representation on this. For example, I compress the image or I use a feature extractor. And then I get like a sequence of states from both of these processes, the original one and the compressed one. And I maintain the rewards that were accrued during the generation of this data, and I can use those rewards to define my cost function.
All right. So because kind of the way you generate the compressed things is because you had the uncompressed things, so you know what reward belongs to that, and that's how you get the reward.
Exactly. Yeah, right.
So maybe a kind of follow-up to that. Is there a way you think to extend this to rewards free settings and say you plug in a higher dimensional base cost that is the state occupancy itself, for example, or discounted state occupancy? What would this end up in your? What would this end up being in your representation then?
Right. Yeah. So if you have like no reward or no sort of like semantic meaning that is associated with the states, then of course you cannot really like compare processes, right? Because if you cannot compare like individual states, then how are you hoping to compare entire distributions over them? And this has been an eternal problem in representation learning for reinforcement learning. Oh, sorry. So there's some notes by Nan Jiang on state abstractions where he writes quite a lot about matters like this. So somehow like having like a meaningful cost is like a necessity for solving these types of tasks. So it needs to come from either a labeling function or a reward function or something like that. Yeah. So I guess like maybe like getting back to like Herke's question that is also relevant to this is that in these experiments, in these block Markov chain experiments, the cost function that we used was the following, that we had a labeling function that was associating a label 0 with everything except for these wall states, right? So this one had a label of +1, and these ones up there, they had a label of -1. All of the other states are indistinguishable, right? But still, given this very limited labeling function that only is able to distinguish between like very, very few states, you can learn like a pretty accurate representation of the rest of the states as well.
So, but maybe you had a slide where you showed the linearity of the thing. And isn't that also linear in the cost function at that point?
Oh yeah, right. Yeah, absolutely. Yeah, that's really what makes this whole approach click. Yeah, that's the right observation, right? So this objective, right? So this is linear in mu, right? And it's linear in the cost function, which is what makes this a linear optimization problem.
Right. So if both state spaces were small, you could also learn this without C itself, right? And plug in a C sort of as a vector in that space.
Well, it needs to come from somewhere. Yeah. Well,
Right.
so maybe,
Yeah,
maybe let's
yeah,
take
yeah.
this offline. Let's refine this idea a little bit further.
What if you have a if you only have the cost function at some of the states, but not all? Like there are certain states which really matter, but certain states we simply don't know, or let's say even one we would ignore.
Right. So if you look into the details of this algorithm, I guess the cost function appears in the gradient with respect to mu. So it only appears in this update over here, and it can really have like partial observations of the state space as well. So basically what you need is the cost function to be well defined in the states that mu samples from, right? And then you can use some importance weighting tricks to somehow like fill out the rest of the entries of the cost function as well. I'm not sure if that's like a perfectly satisfying answer, but the cost function is only necessary for computing some of these updates, and that allows some partial observation. Those updates can handle that.
So I was curious about the role of sampling from mu, because you have mu explicitly throughout. So
yeah.
What's the reason for sampling from it?
Right, yeah. So the reason is that this is how I wrote the slides with sampling from mu. By the time we finished the paper, we realized that actually we don't need this at all. And in the actual paper, in the actual implementation, we just calculate this expectation with respect to mu exactly. So you can do either that, just calculate the exact average, or do sampling. Yeah, both work. All right, thank you very much.